An international collaboration of theoretical physicists, including scientists from the U.S. Department of Energy's Brookhaven National Laboratory, BNL, and the RIKEN-BNL Research Center, RBRC, has published a new calculation relevant to the search for an explanation of the predominance. The collaboration, known as RBC-UKQCD, also includes scientists from CERN, the European Particle Physics Laboratory, Columbia University, the University of Connecticut, the University of Edinburgh, the Massachusetts Institute of Technology, the University of Regensburg, and the University of Southampton. They describe their result in a paper to be published in the journal Physical Review D and has been highlighted as an editor's suggestion. Scientists first observed a slight difference in the behavior of matter and antimatter, known as a violation of CP symmetry, while studying the decays. While the standard model of particle physics was pieced together soon after that, understanding whether the observed CP violation in kaon decays agreed with the standard model has proved elusive due to the complexity of the required calculations. The new calculation gives a more accurate prediction for the likelihood with which kaons decay into a pair of electrically charged pions versus a pair of neutral pions. Understanding these decays and comparing the prediction with more recent state-of-the-art experimental measurements made at CERN and DOE's Fermi National Accelerator Laboratory gives scientists a way to test for tiny differences between matter and antimatter, and search for effects that cannot be e. The new calculation represents a significant improvement over the group's previous result, published in Physical Review Letters in 2015. Based on the standard model, it gives a range of values for what is called direct CP symmetry violation in kaon decays that is consistent with the experimentally measured results. That means the observed CP violation is now, to the best of our knowledge, explained by the standard model, but the uncertainty in the prediction needs to be further improved since there is also an opportunity to reveal any sources of matter-antimatter asymmetry lying beyond the current theories de. An even more accurate theoretical calculation of the standard model may yet lie outside of the experimentally measured range. It is therefore of great importance that we continue our progress, and refine our calculations, so that we can provide an even stronger test of our fundamental understanding, said Brookhaven Lab theorist Amarjit Soni. Matter-antimatter imbalance, the need for a difference between matter and antimatter is built into the modern theory of the cosmos, said Norman Christ of Columbia University. Our current understanding is that the present universe was created with nearly equal amounts of matter and antimatter. Except for the tiny effects being studied here, matter and antimatter should be identical in every way, beyond conventional choices such as assigning negative charge to one particle and positive charge to its antiparticle. Some difference in how these two types of particles operate must have tipped the balance to favor matter over antimatter, he said. Any differences in matter and antimatter that have been observed to date are far too weak to explain the predominance of matter found in our current universe, he continued. Finding a significant discrepancy between an experimental observation and predictions based on the standard model would potentially point the way to new mechanisms of particle interactions that lie beyond our current understanding, and which we hope to find to help to explain this imbalance. Please support my channel to grow by pressing subscribe button and the bell icon. We will notify you technological news. Thank you.